Can rising CO2 levels help plants thrive while still harming the planet? That's the strange contradiction at the heart of the global greening paradox, which observes that while increased carbon dioxide, a major driver of climate change, is warming the planet, it is also stimulating plant growth worldwide. Satellite data over recent decades show that vegetation cover has expanded across large regions of the Earth, especially in arid zones like parts of Africa, India, and Australia. Why? Because CO2 is not just a pollutant, it is also a raw material for photosynthesis. And many plants grow faster when more of it is available. So paradoxically, the same gas that is destabilizing ecosystems is also making them greener. For now. But is this greening actually good? Not necessarily. While some plants benefit short-term from higher CO2, the long-term effects of climate change, heat stress, droughts, extreme weather, soil degradation, and species imbalance may ultimately reduce biodiversity and harm ecosystems. Plus, faster green plants can store more carbon temporarily, but can't keep up with emissions indefinitely, and many forests risk becoming net carbon sources as they suffer from wildfires and disease. Analogy, it is like giving a plant steroids. It may grow quickly at first, but the underlying damage mounts over time. The global greening paradox reminds us that not all growth is good, and that apparent benefits can mask deepening instability in Earth's climate system. Is the same rise in atmospheric CO2 that drives a measurable greening of Earth's vegetation also fueling the very climate extremes that threaten plant and ecosystem health? Satellite data and long-term flux measurements reveal that elevated CO2 enhances photosynthetic rates and water use efficiency, boosting leaf area and biomass across many biomes. Yet at the same time, CO2-induced warming, altered precipitation patterns, and increased frequency of heat waves and droughts undermine these gains, leading to forest die-offs, grassland degradation, and biodiversity loss. So far, so good, until we recognize that global greening is neither uniform nor guaranteed. The CO2 fertilization effect depends on sufficient water and nutrients. In many tropical and boreal regions, phosphorus or nitrogen limitations blunt the response. Meanwhile, warmer temperatures increase evapotranspiration, reducing soil moisture and counteracting the enhanced water use efficiency in plants. In Mediterranean and semi-arid ecosystems, the net effect can shift from greening to browning within years as water stress overrides any CO2 benefit. At its core, two intertwined mechanisms drive the greening. Photosynthetic stimulation, elevated CO2 raises the carboxylation efficiency of rubisco, increasing carbon assimilation and growth rates in C3 plants. Improved water use efficiency, higher CO2 reduces stomatal aperture for the same CO2 uptake, cutting transpiration and helping plants conserve soil moisture. Yet even this mechanistic view conceals deeper complexities. Soil nutrient cycles respond to warming and moisture changes, altering microbial activity and the availability of nitrogen and phosphorus. In some forests, warming accelerates decomposition, releasing nutrients that temporarily boost growth, but also depleting soil organic matter, undermining long-term fertility. Furthermore, invasive species and fast-growing weeds often capitalize on CO2 enrichment more readily than native flora, shifting community composition and ecosystem function. At even finer scales, extreme events punctuate the trend. Heat waves can induce widespread hydraulic failure in trees, causing mortality that reverses decades of CO2-driven carbon uptake in a single season. In the Arctic, early snowmelt followed by drought can trigger greening in spring, but lead to severe browning by midsummer. Similarly, nutrient-poor tropical soils may show a transient greening pulse, only to plateau or decline as nutrient demand outstrips supply. In essence, the global greening paradox reminds us that increasing CO2 is both a fertilizer and a forcing agent. It can stimulate plant growth where conditions allow, yet it simultaneously amplifies the climatic stresses that threaten those very gains. Like other deep paradoxes, from the size-dependent property paradox to the biological autocatalysis mystery, it underscores the need for multi-scale, integrative models that account for physiology, soil chemistry, and extreme events to predict how ecosystems will truly fare in a high CO₂ world. Rising atmospheric CO₂ enhances photosynthetic rates and water use efficiency in many plants, leading to a measurable greening of vegetated regions worldwide. This vegetation boost can sequester additional carbon, partially offsetting anthropogenic CO₂ emissions and slowing climate warming. However, higher CO₂ also drives climate extremes, heat waves, droughts, and fires that degrade ecosystems and release stored carbon. Thus, CO₂ both fertilizes plant growth and amplifies environmental stressors that undermine long-term ecosystem health. Satellite observations since the 1980s show a 6% increase in global leaf area index, largely attributed to CO₂ fertilization in expanding forests and croplands. It is like overfeeding a child who grows rapidly at first but then develops diabetes and organ damage from the same excess nourishment. CO₂ fertilization refers to the direct biochemical enhancement of photosynthesis, when plants absorb more carbon dioxide, promoting growth under adequate water and nutrients. Climate stress encompasses indirect effects, higher temperatures, altered precipitation, and extreme events that can limit or reverse this growth benefit. The paradox arises because the same CO₂ molecule that boosts carbon uptake also drives the greenhouse effect, intensifying conditions hostile to plant survival. Recognizing this duality is key to understanding why a greener planet may nonetheless face ecosystem collapse. In semi-arid regions, initial greening from CO₂ can be wiped out by subsequent multi-year droughts fueled by warmer temperatures. It is like adding steroids to an athlete. Performance skyrockets, but long-term health suffers from cardiovascular and musculoskeletal damage. At the cellular level, elevated CO₂ increases the carboxylation rate of the enzyme rubisco, reducing photorespiration and improving carbon fixation efficiency. C3 plants, e.g. wheat, rice, benefit most, showing up to 30% faster growth under CO₂ enrichment in controlled experiments. This metabolic shift also improves water use efficiency by allowing stomata to remain partially closed, reducing transpiration. Yet nutrient limitations, nitrogen, phosphorus, and acclimation over time can dampen these gains in natural settings. Air CO₂ enrichment studies reveal that C3 crops under 550 ppm CO₂ yield tilled 20% more biomass, but only when soil nitrogen is adequate. It is like turbocharging an engine. You get more power only if the fuel supply line is wide enough and the engine components can handle the extra stress. Enhanced photosynthesis demands corresponding increases in nutrient and water uptake to build new tissues, creating potential bottlenecks. Soils poor in nitrogen or phosphorus limit the capacity of plants to capitalize on CO₂ fertilization, leading to nutrient dilution in leaves. Similarly, although higher CO₂ reduces water loss per leaf, overall warming can increase evaporative demand, negating efficiency gains. Consequently, the greening effect plateaus or reverses where resource constraints or intensified drought prevail. Tropical forests on infertile soils show minimal greening despite elevated CO₂, while temperate forests on richer soils green more robustly. It is like a factory, increasing production speed but lacking raw materials or cooling systems to sustain the faster output. Rising CO₂-driven warming intensifies heat waves, wildfires, pest outbreaks, and storm damage, all of which can decimate plant biomass abruptly. These disturbances release large pulses of carbon back to the atmosphere, counteracting gradual greening gains. Ecosystem resilience varies. Some biomes recover quickly while others shift to degraded states, e.g. forest to savanna. Thus, episodic extremes impose a non-linear check on the steady CO₂ fertilization trend. The 2019-2020 Australian bushfires burned over 17 million hectares, reversing decades of greening in eucalyptus forests. It is like saving money in a bank that periodically levies massive fees, erasing years of incremental interest gains. Vegetation responses to CO₂ and climate operate through thresholds. Once warming or aridity crosses certain limits, system behavior shifts abruptly. For instance, permafrost thaw under warming liberates soil carbon, fueling further warming and forest dieback. Similarly, tropical rainforest dieback can flip to savanna with lower leaf area and carbon uptake. These feedbacks underscore that CO₂-driven greening may hit tipping points, leading to rapid ecosystem degradation. Amazon models predict a potential tipping point at tilde 3 DEGC warming, beyond which large swaths could convert to grassland. It is like a levee holding back floodwaters until a critical pressure is breached, after which the entire defense collapses. Global greening complicates carbon budget estimates by introducing a semi-predictable sink, yet over-reliance on this sink risks undercutting emissions reduction efforts. Policymakers must account for the transient nature of CO₂ fertilization and the vulnerability of greened areas to climate extremes. Effective climate strategies therefore require aggressive emissions cuts alongside conservation of resilient ecosystems. Otherwise, temporary greening may lull stakeholders into complacency, jeopardizing long-term climate stabilization. IPCC projections include land carbon sink feedbacks, but stress that sink strength declines at higher warming levels. It is like budgeting household finances, assuming an ever-rising stock market that could crash, wiping out perceived gains. Satellite indices, e.g. NDVI, detect greening but cannot distinguish CO₂ fertilization from land use change, afforestation, or recovery from past disturbances. Ground truthing requires extensive field work to untangle local management practices, invasive species, and grazing impacts. Climate models must integrate biochemical, hydrological, and disturbance processes across scales, yet uncertainty remains high in projecting future sink dynamics. Accurately attributing greening to CO₂ versus other drivers is therefore a persistent scientific challenge. Observed greening in China combines CO₂ effects with massive reforestation programs, complicating global analyses. It is like observing a city's skyline brighten at night, but not knowing if it's due to more streetlights, rebuilding projects, or shorter nights. Integrating satellite data, ecosystem experiments, e.g. FACE, and advanced Earth system models will refine our understanding of the greening paradox under higher CO₂ and warming scenarios. Emerging technologies such as drone-based hyperspectral imaging and AI-driven data assimilation promise tighter constraints on sink projections. Managing both CO₂ levels and ecosystem health holistically offers the best chance to harness greening benefits while guarding against collapse. Ultimately, resolving this paradox is critical for navigating the planet's climatic and ecological future. Next-generation NASA missions aim to map global photosynthesis rates in real time, improving model calibration. It is like installing advanced weather stations across a mountain range to forecast both gentle rains and catastrophic avalanches.